And welcome. In this video, we'll be looking at the applications of the Pythagoras Theorem to finding dimensions of a rectangular solid. So we're going to determine in particular the length of the diagonal that is formed in this rectangular solid. And the diagonal that this question is referring to is this slant line that I am marking in red. That is the diagonal that the question is asking us to find. And what you notice is that this diagonal is a part of a right triangle that is formed inside of the rectangular solid. This right triangle that I'm marking in red. Here we go. Okay. All right, so we're going to mark that as well. So we realize that we have a nice right triangle that is formed. This is a right triangle because of the 90-degree that is formed here at the vertex. So we have a right triangle inside of this rectangular solid. And what we need to find is the length of this diagonal. And we realize that this diagonal is the longest length in this right triangle that I have marked out. So we're going to label that as C, which is the hypotenuse. The longest length in any right triangle is called the hypotenuse. So that's C. And we're going to label the base area here as B. So we're going to label that as B, the base of the right triangle. And the height of this right triangle we're going to label as A. Since we know that the height of the entire rectangular solid is 10 inches, and the height of this rectangular solid is the same all around. So this height is going to be the same as this height, which is the same as this height, and is also the same as the value of A, which represents one of the indicated heights in this rectangular solid. So since the height is constant all around, and we know that the height of the rectangular solid is 10 inches, and it stands to reason that A would also be equal to 10 inches. So we have A, which is 10 inches, and we know that B here represents the base of this triangle that is formed inside of this rectangular solid. We're interested in finding the value of C, C being the diagonal of this triangle that I have marked. We're going to use the Pythagoras theorem eventually to find C, but we need some more information before we can apply the Pythagoras theorem to find C. The information that we need is the length of B, which is the base of this right triangle. We already have A, but we do not have B. Once we know B, then we can easily find C. So let us focus on the base of this rectangular solid. What we realized about the base of this rectangular solid is that the diagonal B, so B actually forms a diagonal, and the diagonal B divides this rectangular base of this rectangular solid into two equal halves, and the two equal halves are actually two right triangles with the same dimensions. So this is one triangle here and one triangle here, which are the two halves into which B divides the base. Both of these halves represent right triangles, as represented by the fact that there is a 90-degree formation right here at the vertex of the triangle. So we're going to focus on one side. We only need to focus on one side of the rectangular base, one of the triangular sides, that is, of the rectangular base that is formed as a result of B dividing it into two halves, dividing the rectangular base into two halves. Now, what we know about a rectangle is that opposite sides of a rectangle have the same length. So, of course, that means that since this length is 4 inches, then this length over here is also going to be 4 inches because it is on the opposite side. Right? Opposite sides of a rectangle have the same length, so it means, of course, that this would have 6, but we're not focusing. would have a length of 6 inches, but we're not focusing on that side of the rectangular base. We only need to focus on one side. The dimensions are the same on both sides, so you're going to get the same answer anyways. So now that we have defined the value of this length here of this triangle as 4 inches, and we already know the other dimension of this right triangle, which is 6 inches, we can then easily determine B. B represents the diagonal of the right triangle that is formed right here. So B is the diagonal. So since B is a diagonal, we can find B using the principles of the Pythagoras Theorem. Now we know that the Pythagoras Theorem says that C squared, C being the hypotenuse, which is the diagonal or longest length in a right triangle, we know that C squared is equal to the sum of the squares of the other two sides in a right triangle. This is what the Pythagoras Theorem says. C squared, which is the square of the hypotenuse, is equal to the sum of the squares of the other two sides in the right triangle. So what we're focusing on here right now is simply determining the value of B, because we need the value of B in order to eventually calculate the length of this leading diagonal in the rectangular solid. So in order to find B, we're going to use the principles of the Pythagoras Theorem. So by the Pythagoras Theorem, since B is the longest length, or in other words, the diagonal or hypotenuse, B is the diagonal or hypotenuse of the triangles formed in the base, then it will be equal to the square of B will be equal to the square of the other two sides, which are 4 and 6 inches respectively. So B squared would be equal to 4 squared plus 6 squared. And that is again because B represents the hypotenuse, the longest length in the triangle formed here in the base. So we use the principles of the Pythagoras Theorem to find B, which represents the diagonal in the triangles formed in the base. So B squared would be equal to 4 squared plus 6 squared. And so this means that when we transpose for B itself, B would be equal to the square root of 4 squared plus 6 squared. So B is equal to the square root of 4 squared plus 6 squared. And that is because in order to get rid of the power of 2, which is the square on B, we would take the square root of B squared. The square root of any squared term gets rid of the power of 2. So we're left with B equal to the square root of 4 squared plus 6 squared. Of course, what you do to one side of an equation, you have to do to the other side to maintain balance. So by transposition for B, B is equal to the square root of 4 squared plus 6 squared. So now we can easily find B, which is the base of the triangle I've highlighted in red inside of the rectangular solid. So B is going to be equal to a square root of 4 squared, which is of course 4 multiplied by 4, which is 16, and 6 squared, which is 6 multiplied by 6, which is 36. So what we now have here is that B will be equal to the square root of the summation of 36 and 16. So we're just going to simplify here by finding the sum of 16 and 36, and the sum of 16 and 36 is 52. So B is going to be equal to the square root of 52. Rounded to the nearest tenth, square root of 52 is going to give us 7.1 inches. Right? The dimensions of this solid are in inches, so this will be 7.1 inches. So what we have just found here is the value of the base of this triangle that I've carved out in red inside of the rectangular solid. The base of that rectangular solid is B, which is 7.1 inches. Now, since we know that B is 7.1 inches, then we now know A, 10 inches, which we earlier discussed, and now B, 7.1 inches. So we can now easily find C. Here, which I'm marking in blue, we can now easily find that C. So C squared, based on the Pythagoras theorem, C squared is equal to A squared plus B squared. And since we know that C by transposition is going to be equal to the square root of A squared plus B squared, by virtue of the fact that in order to get rid of this power of 2 on the C squared, we will take the square root of C squared. So the square root of C squared gives us C. But what you do to one side of the equation, you have to also do to the other side. So we take the square root of the right-hand side of the Pythagoras equation here. So we get a square root of A squared plus B squared on the right side. So now we can easily compute C, which is the length of the diagonal, the main diagonal here that we're asked to find inside of this rectangular solid. So let us pick up the value of A, which is the height of this rectangular solid, also the height of the right triangle that is formed and marked out in red. So that will be a value of 10. So 10 squared plus B, we just worked out the value of B to be 7.1 inches. So that's going to be 10 squared plus 7.1 squared. And this is going to give us C equal the square root. So let's simplify here now. 10 squared, which of course means 10 multiplied by 10, is going to be 100. Plus 7.1 squared, which is 50.41. So C is going to be equal to the square root of 100 plus 50.41, which is 150.41. And that's the missing length. The square root of 150.41 inches. That is the length of the main diagonal marked using the value of C here in the right triangle. That right triangle is the right triangle that is formed inside of the rectangular solid. So when we take the square root of 150.4, that square root of 150.4 would give us the approximate value of C. So we take the square root of 150.41, and the square root of 150.41 here will give us 12.26. So approximately 12.26, but I'm going to round this to the nearest tenth. So 12.26 rounded to the nearest tenth is going to be 12.3. So our answer is 12.3 inches. So the value of C here we've worked out to be 12.3 inches. 12.3 inches represents the length of the diagonal of the rectangular solid. Thank you very much for your time, and I hope this was very helpful to you in developing a solid understanding of how to use the Pythagoras theorem to find dimensions of rectangular solids, and it's the same principle that is applied in similar three-dimensional objects. Thank you, everyone. See you again soon, and I'll be doing another problem where we apply the Pythagoras theorem to find the dimensions of three-dimensional objects. objects. See you soon.